Hashing, unlike encryption, has nothing to do with confidentiality, but rather integrity. Integrity that messages that are sent are the messages that are received. Hashing makes sure no bits have been changed either accidentally or maliciously in transit. In a little bit, we'll discuss how it also protects data at rest. Hashing algorithms have a few characteristics. Variable length input, fixed length output. You could feed the Declaration of Independence into a hashing algorithm or just your name. In each case, you'll wind up with the same sized output hash, also called a message digest. If one bit in the input changes, the resultant hash is completely different. You can't go back. Let's say you take a banana, some strawberries, milk, vanilla syrup, and more, and put it in a blender. While enjoying your smoothie, you think to yourself, I wish I could have that banana back. Sorry, you can't get the banana back. You might know the process of taking a banana out of a smoothie and reconstructing it, but it doesn't mean that it could be done. Quick, think of two numbers that multiply together to get 100. 25 times 4, 50 times 2, 20 times 5, 10 times 10. Well, I was actually thinking of 100 times 1. You don't know what two numbers I picked and subsequently threw away. Hashing involves doing some calculations and throwing away the inputs, doing some more math, throwing away more inputs in the same process. Hashes are called one-way functions because it's not feasible to try all possible combinations in a realistic amount of time to go back the other way. While it might be easy to go through all numbers that multiply together to get 100, when multiple rounds are used and one output is at the end, how can you go back, trying all possible combinations? Let's say I multiplied that 100 by 8. Now we've got 800. And now you have 2 rounds of inputs to get back to the original factors of 100. Besides, I'm only using multiplication. Hashing algorithms, of course, are much more mathematically intensive. The way passwords should always be stored in some database is in hashed format. This prevents someone from reading and understanding the password while it's being transmitted or stored. When you log into a local machine or a remote machine, you enter your password, which is subsequently hashed and compared after it's being transmitted to the stored hash on the authenticating system. The same thing happens when you enter your PIN at the ATM. Recent data breaches have brought to light the fact that some entities were storing passwords in plain text, a security 101 no-no. If you've ever downloaded a file from the internet, you might have seen its hash next to the link you clicked. If you run your downloaded file through the same hashing algorithm and get the same message digest, you know that you got the file intact, and that no bits were changed accidentally or maliciously in transit. The weakness of a hashing algorithm, or when a hashing algorithm should be retired, is when it becomes easy to find multiple inputs that produce the same output message digest. This has been the case for both MD5 and, more recently, SHA-1. SHA-256 is the hashing algorithm in great usage today. The output of 256 bits, which is why this version of SHA-2 is called SHA-256, makes it more secure. SHA-1, by comparison, just used 160 bits. If a password database of weak hashes is stolen, the attacker doesn't need your password. The attacker just needs to find some plain text that hashes into what your password was hashed into. In a future course, we'll explore rainbow tables, which allow hackers to do just that. We'll also learn something called SALT, which defeats these rainbow tables.